So here we have exercise 20.41, part B. Now when you look at the reagent and the product here, you'll notice two things. First, you have a terminal alkyne. You have a triple bond at the end of a carbon chain. It's called a terminal alkyne. And we saw how you can use that to create either an aldehyde or a ketone using some sort of hydration. And you'll get, if you do anti-Markovnikov addition through hydroboration oxidation, then you'll get an aldehyde, and if you do Markovnikov addition through acid-catalyzed hydration, you'll get a ketone. And if all of that sounds like gibberish in a foreign language, I encourage you to go back and watch the video on synthesizing aldehydes and ketones, where we talk about those terms. And they're listed, the reagents are listed separately in a table. So that's the first thing. We have a terminal alkyne. The other thing to notice is the difference between these molecules on the left and on the right. First thing is you have a lot of pi bonds here. You have a triple bond, so that's 2 pi bonds and a sigma bond. And then you don't have any pi bonds in the branch on the right. So that's a sign that you've done some sort of an addition reaction. And the truth is, for every addition reaction you do, you have 1 less pi bond. So we probably did 2 addition reactions, whatever else we do. Okay, that doesn't narrow things down too much. The other thing you'll notice, though, is that if you count the carbons on the left, you have 1, 2 outside of the ring, which is constant. Here you'd have, say, 1, 2. And you'll notice that you've added a new carbon. So this carbon here, you have a new carbon-to-carbon bond that's not there in the original molecule. That helps us because that really narrows down what we need to do. There aren't that many ways that you can form a new carbon-to-carbon bond. So when you see that you need to do that, that gives you some direction, a sense of direction in terms of what you want to accomplish. Okay, now in a previous video, in the video for part A for this, we went through the different types of carbon-to-carbon bond forming reactions you can have and when you use them. You'd recognize that here you're forming a carbon-to-carbon sigma bond. It's just 1 bond there. The first bond you ever form is a sigma bond. And you make a new carbon-to-carbon sigma bond with a Grignard reagent. Right? The other ones were Diels-Alder if you make a ring, Friedel-Crafts alkylation or acylation if you're adding something, a new carbon branch onto benzene, or the Wittig reaction where you're creating a carbon-to-carbon double bond. Here we just want the sigma bond, so we're going to do a Grignard reagent. When you try to think of what you want your Grignard reagent to be, look at the carbon chain that you're trying to add, replicate that, and then just add magnesium bromide. You want the carbon bonded to the magnesium because it's the difference in electronegativity between the carbon and the magnesium that turns the carbon, which is really here like the CH3, that's what that is, it turns that into a nucleophile with a full negative charge. And the magnesium, stabilized by the bromine, has about a positive 1 charge. So okay, whatever else we need, whatever else we're going to do, we're going to have to use a Grignard reagent to create that new carbon-to-carbon sigma bond. So let me use this bottom one because it's a little clearer. Now, the only thing is, when you do a Grignard reagent, the carbon is a nucleophile. It's only 1/2 of your picture. In addition to the nucleophile, you need an electrophile for it to attack. Oops. You need an electrophile for it to attack. And so, what type of an electrophile can you use? Well, the chapter we're in would give you a hint, but also the fact that we have that terminal alkyne would give you a hint. Let's say going backwards, we think, okay, well, I know I need an electrophile, but I'm not really sure what electrophile to use. If you go back to this starting material, you say, okay, terminal alkyne, I know I can make, I don't know if it'd be useful, but I know I can make an aldehyde or a ketone out of that. And then it hits you. Aldehydes or ketones are good electrophiles. Now we want carbon number 1 to be the good electrophile, because that's where our Grignard reagent is going to be attacking. So we want the carbonyl to be on carbon number 1. Okay, well, we're going to add H and OH. We have two possibilities for where they can attach. Carbon number 1 is bonded to 2 carbons, so it's secondary. Carbon number 2 is bonded to just 1 carbon, so it's primary. Carbon number 1 is the more substituted carbon. And if we want the OH to go there, if we want the OH to go to the more substituted carbon, then we need to do Markovnikov addition. We need Markovnikov addition of H and OH. And the recipe for that was acid-catalyzed hydration. So you'd have sulfuric acid, mercury 2 sulfate, and water. And that will turn that terminal alkyne at first just into an enol. So you'd still have carbon number 1 and 2 here. You still have 1 pi bond to them, but you use the glue from the other pi bond to add an OH onto the more substituted carbon and an H onto the less substituted carbon. And this is called an enol because you have a double bond, so ene, and an alcohol, so all. And again, this is Markovnikov addition because the OH went on the more substituted carbon. The carbon bonded to more carbons. Well, these enols are always existent in equilibrium with a keto form. There's something called keto-enol tautomerism, and that's where a hydrogen just moves around. Hydrogens and electrons move around within the same molecule. So the hydrogen that's attached to that oxygen can sort of hopscotch to this carbon down here at the same time that the pi electrons move toward the oxygen. And so that gives us our ketone. That's called keto-enol tautomerism. And so the overall story of that reaction is that you took a terminal alkyne, you did acid-catalyzed hydration, and you ended up with a ketone. And we've seen that before. We've seen it in the video we made for synthesizing aldehydes and ketones. In this table that we discussed, we saw that if you have a terminal alkyne, you can add sulfuric acid, water, and mercury 2 sulfate, and it'll turn it into a ketone. Okay. So, now we have this ketone. Well, let's look back at our overall goal and see where we are in relation to it. I'm going to erase these hydrogens so they don't distract us. Well, we made that ketone just so that we made the ketones so that our nucleophilic Grignard reagent could attack it. But here we run into something of a difficulty. What if you try to do that Grignard reagent? Well, if you try to do the Grignard reagent, if this attacks this molecule, this negative carbon can attack the carbonyl, the pi bond breaks, goes on to the oxygen. You would end up with a new CH3, that's that Grignard reagent that added only 1 bond to the oxygen, which now has a negative charge, and then you can just add some water to do a proton transfer. So these would exist in equilibrium. The negative oxygen can attack one of those slightly positive hydrogens. Okay, so this is what we get following our reasoning so far. And it's close. It's definitely close to what we wanted. But unfortunately, the OH is on the wrong position. Right? In this one, we have the 2 methyl branches just like we wanted, but the OH is on the middle one instead of on the end. It's on carbon number 1 instead of on carbon number 2. Now, you do have a couple choices here. You could, for example, do an elimination reaction. Oops. You could, if you remember from Organic Chemistry 1, you could do an elimination reaction by adding a strong acid. So this is a bad leaving group, so you have to turn it into a good leaving group. And what you would want to remember from Organic Chemistry 1 is that concentrated sulfuric acid, which is kind of a nasty thing, could give you this double bond. So if you wanted to see how that would work, sulfuric acid has this sort of sulfur carbon version of carbon dioxide, up and down with oxygens and double bonds, and left and right oxygens with single bonds with two hydrogens on the end. The oxygen here can use one of its lone pairs and slight negative charge to steal the hydrogens, which go onto there. That turns that into a good leaving group. So now we have this with an OH2. So that's an awesome leaving group, and what we'd also have after that step is the conjugate base of sulfuric acid. The leaving group can leave, so that happens in a separate step, which is why it's E1. If you recall from Organic Chemistry 1, oops. That leaves us with a carbocation, and the conjugate base of the sulfuric acid, weak as it is as a conjugate base, can come in, and because there's already a full positive charge there, it can act as the base in an elimination reaction and steal one of the beta hydrogens, like we discussed in part A for elimination reactions. Those electrons can go toward the positive charge, and you'd end up with this product that we have down here. And actually, just to make it consistent with the drawing in the original that we're going toward, let's say that hydrogen is symmetrical with the beta hydrogen up here, because there's a line of symmetry down this molecule. So just so it looks similar to the product we want, we'll take that, and these pi electrons go here. And now we have an alkene, and we can put the OH on the less substituted carbon of that alkene by doing anti-Markovnikov addition of H and OH. So anti-Markovnikov addition of H and OH is hydroboration oxidation. So BH3 followed by THF, sodium hydroxide, and hydrogen peroxide. So that's one possible way that you could make that product. There's sort of a snafu there for a second. So notice, this is anti-Markovnikov because you have two carbons here. The one on the top is only bonded to one other carbon. The one on the bottom is bonded to 1, 2, 3 other carbons. So the top one is the less substituted one. Anti-Markovnikov addition puts the OH on the less substituted carbon, the top one. And you also add an H there. But because this is a skeletal structure, that doesn't have to be drawn. And this reaction is one we've talked about at length in our previous videos, which is why I mention it only quickly here. So that's one possible synthesis. Let's write that out, the steps for that all together. The first step was to do this Markovnikov addition onto the terminal alkyne. So sulfuric acid and water catalyzed by mercury 2 sulfate. And once we had that, that gives us our ketone that turns the terminal alkyne into a ketone. Once we have the ketone, we can react it with our Grignard reagent to get the new carbon-to-carbon bond that we saw. So in that case, the Grignard reagent was methyl magnesium bromide, so CH3 and GBr. After we did that, we added some water
because after the Grignard reagent reacts, it leaves the oxygen with a negative charge, so we added some water. And then we felt a little stuck because the OH was on the wrong carbon. So we sort of had to walk it over, first by doing an elimination reaction. And since we had a bad leaving group, we had to use a strong acid. The strong acid first turns it into a good leaving group and then acts as the base for the beta hydrogen. So it's an E1 reaction. And once we had that alkene, we just had to add the OH on in an anti-Markovnikov way, so that it went to the less substituted carbon, and that was with hydroboration oxidation, which happens in 2 steps. So first, BH3 in THF, and second, sodium hydroxide, hydrogen peroxide. So that's one possible synthesis for this. And you could actually do a shorter synthesis if you were a little creative. There's a shorter way to make this happen. What if, at this point, instead of, and I realize this takes a little bit of vision to see this, but what if we do the oxidation and we suddenly realize, oh, if I use a Grignard reagent, then the OH is on the wrong carbon. What's another way that I could make the molecule that they want? The molecule they want is this here. That's what they're asking us for in the problem. So how can you make this transformation? Well, you could skip from here straight to this double bond. You could skip from the alkene, from the ketone to the alkene in one step by doing a Wittig reagent. So a Wittig reagent allows you to turn a ketone or an aldehyde into an alkene, which is what you see here. This has a new carbon-to-carbon bond there. So you'd look for the group that you want to replace the oxygen with, and that is a CH2, and then just double bond that to the triphenylphosphine. So that's your Wittig reagent, and that will replace the ketone with that carbon. And then, just one more step. You can do the hydroboration oxidation. So you can add the OH on in an anti-Markovnikov way, so BH3 and THF, followed by sodium hydroxide and hydrogen peroxide. So that's much fewer steps. Let's compare the 2 possible syntheses side by side. In both of them, you have to do this Markovnikov addition of H and OH. You need that in order to form this ketone out of the terminal alkyne. Let me clean this up a little bit so we can see this a little better. In order to turn this terminal alkyne into the alkene, you have to do the acid-catalyzed hydration, no matter what, in both of these syntheses. So that step stays the same. But if instead of doing a Grignard reagent, we see the possibility of a Wittig reagent, well then, we just have to do this one step, and that replaces these 3 steps. Those get the same thing done. At the end of both of those processes, you end up with this molecule here. In the Wittig reagent, in just one step, and the other way we used the Grignard reagent, water, and then concentrated acid, and through an E1 mechanism that ended up getting us that same molecule. And then we just do the hydroboration oxidation, which we have to do in both of them. So the third would be
borane and THF, and followed by sodium hydroxide and hydrogen peroxide. So really the Wittig reagent is the more efficient synthesis here. Remember, with every reaction, no reaction is going to give you a 100% yield. So the more reactions you do, the less efficient your synthesis is going to be. The more whatever you make is going to cost to people, and maybe the less money you can make off of it yourself. Or the less capable people will be for making it to save people's lives, because it won't be as cost effective. So there is almost always more than one way to make a synthesis happen. So long as your synthesis is correct, I will not take points off. You don't have to have the most efficient synthesis. That's a goal for maybe your own professional life to do that. But for this class, so long as you can make the synthesis happen, that works for me. The categories of reactions here are very few. There are really only two. There's addition of H and OH. I'll highlight those in purple. Now you can have Markovnikov or anti-Markovnikov. So that's addition of H and OH in purple. And then there are new carbon-to-carbon forming reactions, either Grignard or Wittig. So those are the two big categories we saw here. Like we saw in the previous one, in A, the elimination reactions are really important. They're a huge category of reactions that you would have spent a whole chapter on in Organic Chemistry 1, and that are a really crucial thing if you're not familiar with to review. And so if you're not familiar with those, let me know. I'll send you the videos that I have made for those for the Organic Chemistry 1 people. It's really worth going over. And there will definitely be both E1 and E2 reactions. There could be those reactions on this test. The E2 reactions, you have to worry about the skinny base and the bulky base, and the E1 reaction could happen with a strong concentrated acid like we saw here. Other than that, this thrilling problem ends here with either one of these two.